Welcome to the Bruker Optics Applications Laboratory in Ettlingen, Germany. My name is Jürgen Sawatzki. Today, we would like to present to you a real-time live demonstration of a Raman imaging measurement with the new SENTERRA II Raman microscope. Before we will start with a live demonstration, let's have a look at the concept and features of the new SENTERRA II. The SENTERRA II is a very compact microscope and has been designed in a way that it has a very high degree of automation and the software-guided workflow. This concept is only possible because the system has a permanent alignment of the wave number axis. So the user don't have to care about any interaction with calibrations. Automation is also provided by the instrument test, and the complete system provides comprehensive validation. Let's have a look at the video wizard of the SENTERRA, which guides the user in a very straightforward way through the measurement routine. So the first step is to inspect the sample in the area of interest. The next step, the pictures are taken of the area of interest. Prior to the measurement, the area of interest can be checked with a real-time spectrum display. Measurements can be adapted by the laser wavelengths and other parameters, such as the grating and apertures. And in the further step, the measurement area and grid is defined, either a grid or a line or points, and then finally the measurement is run. The result can be the so-called Raman image, where the different colors are representing different areas of Raman spectra, and these Raman spectra can be generated in a simple way by just integration of the spectra of the certain peaks or areas, but also other means like cluster analysis, partially square algorithm, or component regression, and further means are available for the visualization of your result. The next step may be the use of libraries for the SENTERRA II. More than 2,800 spectra are available for spectral identification. And let's have a look to the SureColor technology. This patented feature provides a very high stability of the wave number axis, and at every stage of the instrument procedure and use, the system is calibrated. So, for instance, if the laser is changed or the grating is changed or any apertures, the system keeps track of the calibration. The user do not have to care about any issues with calibration. And as further results, there is a reliable detection of small Raman shifts without any interaction of the user. You will receive a reproducible quantification, accurate substance identification with your searches, and artifact-free spectral subtraction. The system also is equipped standardly with an instrument test, which is automated. For this automated test is using a validation plate, which is equipped with ASTM and from OIR and USP conform test samples like paracetamol or calcium carbonate and polystyrene. The system is completely compliant to GMP, GLP, and 21 CFR Part 11, and also validation services are available from the Bruker Service Department. So the SENTERRA meets all the requirements in the model lab of today. Let's now focus a little bit on the performance of the spectrometer part. So the system can deliver up to 100 spectra per second for fast Raman imaging procedures. It provides gratings which can result in resolutions up to 1.5 wave numbers, and all spectral ranges provides full range of all gratings. The lasers which can be used are 3 at a time in the dispersive range, so it can be a 532 nanometer laser, 633, and 785. And as a fourth option, also by coupling the system to the FT Raman system, 1064 nanometer excitation for fluorescence-free spectra are available. So SENTERRA II is really prepared for challenging research applications. Here we have a routine measurement of a fast Raman imaging of a polymer laminate. This system consists of 3 layers: polypropylene, polyamide, and polyethylene terephthalate. And the image has been acquired with 50 milliseconds spectral resolution and about 0.75 step width at full spectral range. Here we have an example measured with the high resolution grating. It shows the classical example of carbon tetrachloride, and this band at around 460 wave numbers is the total symmetric stretch of this compound, and it's nicely separated in different isotope splits of the different chlorine isotopes. A further important feature of the system is the high precision encoded motorized stage. Here we see a visual picture taken with 100x objective of a ultra-high precision chess grid. It shows a silicon substrate with gold layers. The squares are 1 micrometer in diameter. And with this encoded motorized stage, with this high precision and minimum step width of about 50 nanometers in XY direction, it's possible to produce a very fine and precise overlay of a Raman image. Look at the congruence of the picture and the Raman image, providing a very high precision movement of the stage across the area. So in the next step, we will have a closer view to the SENTERRA II. SENTERRA II can be equipped with sample very easily. Today we will measure a pharmaceutical tablet. It's a painkiller tablet with a 20x objective. And what we have to do is to focus with the joystick the area of interest. Then we tune the light, and then we move across the sample and navigate to the area of interest. And finally, when we have got the area of interest, the safety cabinet is closed for laser safety. There's no need for safety goggles. And in the next step, we will move on to the Opus software and do our live demonstration of our measurement. So we'll now switch to the Opus software. So here we have the live picture of the Opus software. Again, I can move around with my joystick here. And also with the Z position, makes pictures sharp enough. And what we can do now is we can just take a picture, a snapshot of the area of interest. So here we have the area of interest. We can just make a small measurement, how large it is. It's a range of 300 micrometer. This is the field of view of the 20x objective. So in case we would like to have a larger view, we define a larger preview image, can be the entire tablet. In this case, we have a little bit enlarged the field of view. I will collect the image by now. And we have a collection of 4 windows. And of course, we have the chance to move around also with the mouse by just clicking on the area of interest. And we can also switch back to the other image if we would like, or again back to the other image. And in the next step of the video wizard, we will get the parameter settings side. So here we have lots of options to tune our experiment. We can select the appropriate laser wavelengths. So selection, changing of the laser is within 1 minute, less than 1 minute, and then you will see the spectra popping up with another wavelength. We'll stay for this experiment at the green laser line. We can tune the laser, apertures, and also the measurement time for this fast imaging measurement. I will reduce the measurement time to about 50 milliseconds, and we do about 1 co-addition to shorten the measurement time a little bit. So in the next step, I push this live spectrum button here, and then we will see a window popping up showing us the area which we have taken by the snapshot. And then, of course, we will see the real-time live spectrum in a minute. So laser is on, and then we see on the low end here the real-time spectrum display. Also the laser which flashes on the surface, and where the red crosshair is and the white crosshair, we will target the sample. So if I move around a little bit, let's say to the left, spectrum will of course change. And I think we are content with the performance of the spectrum. We go out, and then in the next step, on the next page, we have the possibility to define our points of interest. It can be a grid or a line or different points. And the upper row is for the surface measurement, and the lower row is also for depth profiling in a grid manner or line manner and so forth. There are also possibilities for different routines. We have here the fast mapping grid mode, and here the point-by-point mapping grid mode. For our experiment, we will provide the fast mapping grid mode. I will now here define a grid. Let's say, let's just go here and define in this area a grid of interest. Put about 40 points in the x direction and about 25 in the y direction. And as one can see here, the difference between the measurement spots are in the range of 5 micrometers. So once we have defined the grid here, we are ready to proceed to the next page. So we could check about the parameter settings. As we have seen here, we have about 50 milliseconds integration time and so forth. And then we'll start the measurement. Here we have the progress bar showing us the progress. On the lower side here we have the spectra which are appearing point by point, line by line. And at the lower end you see the spectra which are collected. And this line here at around 1700 wave numbers is integrated, and you see here the intensity of this line. So in this area, we have a high concentration of this compound, which shows us a line in the range of about 1700 wave numbers. We also can have a look to the live view of the laser. So now the laser is really fastly moved across the area of the sample, line by line. And line by line, also the complete Raman image is collected. So the minimum measurement time or time resolution is about 10 milliseconds, so up to 100 spectra per second. And the limitation is only, I think, by the movement of the stage, which of course needs some time. Depends on the area, of course. If you have a small area, the measurement will be finished quite soon, whereas if you have a large area, maybe the complete tablet, the traveling of the stage needs a little longer, of course. So we have to wait about, I think, two minutes. So once it is ready, with quite about 1,000 data points, we either have the chance to end the video with that or to repeat the measurement. We maybe repeat the measurement, and then we will get a file, a result file here, which shows us different windows. The lower window shows us the spectra window, so we can click here and see different spectra. And on the left side, we see a chemical window. We have a chance here to have different options here. Here we 2D contour plot, and of course you will see different spectra now. And in order to sort out the different kinds of spectra, there is a possibility, for instance, to do some component regression, or as I've mentioned before, some a partially square processing. Today we will use the cluster analysis for the sorting of the spectra. What we have to do is to follow up the progress here, so we can load a method, which we don't have at the moment. So we just put our reference spectra inside of our path here. And then the next step, we have to set the parameters. It can be either no preprocessing, or in this case, we do some normalization with a chance of interactive region selection. So we get rid of this kind of noise here a little bit. Maybe also this valuing is not so interesting. So then we will say OK. And the only thing we have to do is to push the button for the analysis. So it has been done already. The next step, we will have a look at the report. And I would say we will assume that there are 3 different classes. This is the painkiller, and with this assumption, we will just put in this number of classes. And if we push the button here, Store Trace, another trace will be stored here in this file. So I will store the trace here. Then we will remove this window here. You see here, this is the different areas of interest. So we can, for instance, we can make this a little bit more prominent. I will remove the spectra which are here and just push one spectrum here and one in the blue area and one maybe here in the white area. And you will see that we will gain 3 different spectra. So what we have to do is we can just have a closer view to it. Okay. And next, I would like to show to you another tool for the visualization. So we will do a simple integration of our compounds. For this, let me just move around a little bit the spectra for better visualization. So I will put this in this area here. We will just change a little bit the colors. Maybe here we will go to blue. Yes. And then we will integrate the lines. There are different tools. The easiest way is just to double-click here and generate an area for the integration. So first we will integrate this band here. This is done simply by a mouse click with a right click. You go to integration and say integrate. And then you see the distribution of this line across the area, high intensity here. So we'll have a strong band here. Maybe shift this again a little bit upwards. And let's now find some other bands manually for further integration of the other compounds. For instance, we can take another band here, maybe at this range here. I will make this a little bit smaller here of this blue spectrum here. Again, I have to click here with the right click and say integrate. Then again, you see here popping up the 2D Raman image of this line across this area. And finally, we will do integration, let's say here, this band here, maybe it's also quite interesting, quite strong. So again, we do some integration. And you see the upper area is occupied by this compound, which is represented by the red spectrum. So question remains, what kind of compounds do we have? Do we have measured in this area? So what we could do is to do some kind of library search just within this window here. I click here with my mouse on this with the right click. I got a possibility to do some search dialog here. Here we have search dialog. We can choose about the file limits, so we can sort out maybe this area here and have a look at the search parameters. There are different available. We have here a standard algorithm which can be extended to a mixture analysis. So in this case, it's a pure compound, of course. Or alternatively, we have the chance for spectrum correlation and existing peak tables. We state the standard and say, please do our search. I will just zoom it up for better visualization. Maybe we can zoom it a little bit closer. As you can see, the red spectrum is the extraction of one spectrum here, which compares quite nicely with the reference spectrum, which is coffein. Here we have different information about the library, further information about the compound names, the CAS number, and physical properties. So it's quite identical, quite clear. The heat quality is in the range of 898, so 1000 would be identical. So it's quite clear identification. Okay, we'll close this window and move back to our presentation of the spectra. So we had 3 different integration areas, and now the task would be to combine these 3 integration areas within one picture, and we call this RGB plot. So it's a quite straightforward procedure. One has to push this button here and put in the trace, and then choose the different ranges of interest here. We do put in the 3 integration regions, and then say execute. And here you see the result. these are the three areas combined within one picture. Let's just compare this picture with the similar procedure which we have done in the beginning with the cluster analysis. So for this, we have a chemical image window of the same value as on the left side. So what we have to choose is here the appropriate trace. Let's check out here. So here we have a nice comparison between the right and left procedure. On the left, we have done some integration. On the right, the clustering has provided also a quite nice result. So with this, we will close now the live demonstration. I will summarize our demonstration with the last slide. So let's go to the last slide. Here we have the summary, which tells us that the SENTERRA II is really a system which provides intuitive workflow, essentially by the video wizard, but also by the integrated level of high automation. And one part of the concept is the wavelength calibration, which is valid and acting at any stage of instrument operation. So the user can focus on the measurement task completely and is not hindered by any tedious procedures of calibration and tweaking. And last but not least, SENTERRA also provides a very high spectroscopic performance. Thank you very much.